Hey there, and welcome. Today, we are going to be detectives. Seriously, we've got this really cool physics puzzle pulled right from an AQA exam paper, and we're going to crack it together. You ready? Let's get into it. So check this out. This is our mystery. On the left, you've got a plastic rod just sitting on a balance, and it reads 100.25 grams. Simple enough? But then, look at the right. Someone brings a second rod close to it, doesn't even touch it, and suddenly the reading on the balance goes up. How does that even work? How do you make something heavier using some kind of invisible force? Now, this isn't just some random brain teaser I found online. This whole thing comes from question 5 of an actual AQA GCSE Physics paper. So we're going to treat it like a real case and break down every single clue to figure out the physics behind what looks like magic.
Okay, so before we can solve the main puzzle, we have to understand how the scene was set. The whole experiment kicks off by creating static electricity. So let's take a look at the first part of the question.
Here's our first official clue, straight from the source. It tells us flat out, the rod becomes negative and the cloth becomes positive. The big question is, why? What actually happened there? To figure this out, we need to zoom way in, right down to the atomic level.
You know, the entire secret to static electricity, the whole shebang, it all comes down to these tiny little guys, electrons. They carry a negative charge, and the most important thing to know about them is that they are not glued down. They can, and do, jump from one material to another. So this is what's really going on. When the student rubs the cloth and the rod together, that friction gives everything a little boost of energy. This energy is just enough to let some of those negatively charged electrons leap from the cloth onto the rod. Now think about the cloth. It just lost a bunch of its negative charges. Since it started out neutral, it's now left with more positive charges than negative ones. And that's it. It now has an overall positive charge. If you were answering this in an exam, the mark scheme is looking for you to say that electrons, which are negative, moved from the cloth to the rod, and because the cloth lost electrons, it became positive. Boom! Part 1 solved. Now we can use that piece of the puzzle to tackle the main mystery. What is going on with that balance? Right, so the paper wants us to explain why that number on the balance went up. I mean, it's weird, right? Nothing is physically touching, but the weight appears to increase. It feels like it shouldn't happen, but this is just pure, awesome physics at work. To crack this part, you just need to know the number one most fundamental rule of electrostatics. It's super simple. Like charges push each other away. They repel. And opposite charges pull together. They attract. That's the law. And it explains everything. Okay, let's connect the dots. We were told the rod on the balance is negatively charged. Now, for it to be pushed down, there has to be a pushing force coming from above it. And according to our rule, a push means repulsion. So the rod in the student's hand must also be negatively charged. Two negative charges, they repel. This repulsion creates a real physical downward force on the bottom rod. The balance feels that extra push and shows it as a higher reading. For the exam, you'd get marks for saying the rods have the same charge, that like charges repel, and that this creates that downward force. And look, this picture just illustrates it perfectly. You can practically see that invisible force. The top rod is literally pushing the bottom rod down without ever making contact. It's this non-contact force that the balance is picking up. So simple, but so clever.
All right, let's switch gears a little. The next question isn't so much about the forces, but more about the quality of the scientific measurement itself. Let's see what they throw at us.
So the question tells us the balance wasn't perfectly calibrated. It had a 0 error. But then it says, doesn't matter for this experiment. So why not? Why can we still trust our result? Any ideas? And here's the key. The whole point of the experiment wasn't to find the true mass of the rod. It was to measure the change in the reading caused by the repulsive force. We only care about the difference between the first and second measurement. So if the balance started a little bit off, that error is there in both readings. When you find the difference, it just cancels itself out. That's it. For a top mark, you'd want to use the word difference or change in your answer. We are on the home stretch now, folks. Let's get into the final part of this physics puzzle. And this one has a much more dramatic ending. Forget the balances for a second. We're talking about sparks now, like a tiny little bolt of lightning. So the scene is, we have our negatively charged rod, and we bring it near an earthed conductor, which is really just a fancy way of saying an object that's connected to the ground and can easily handle a flow of charge. So why does a spark suddenly leap across the gap? To get this, we need to talk about something called potential difference. The easiest way to think about it is like electrical pressure. You've got the rod over here, packed with a huge buildup of extra electrons, and you've got the earthed conductor over there, which is neutral. That creates a massive difference in electrical pressure between them, a very large potential difference. So what happens next is a chain reaction. That huge potential difference is so strong it actually starts to affect the air in the gap. It rips electrons off the air particles themselves, which is called ionization. For a split second, this creates a little pathway through the air that can conduct electricity. And then, whoosh, the electrons on the rod rush across that path to get to the earthed conductor. That sudden massive flow of charge is what we see and hear as a spark. And there we have it. Just like that, the entire mystery is solved. We have officially cracked AQA's question 5, from start to finish. So let's just do a quick run-through of the main principles we used to solve the case. So here are the key codes we crocked today. 1. Static electricity is all about electrons on the move. 2. That charge creates invisible, non-contact forces like repulsion. 3. When you're measuring things in an experiment, sometimes it's the change that really matters, which can make things like a zero error totally irrelevant. And 4. A big enough potential difference can literally rip the air apart to create a path for a spark. From getting a little zap off a car door to seeing your hair stand on end, the physics we just broke down is happening all around us all the time. So I'll leave you with this final thought. Where have you felt that little zap of static electricity in your life? Thanks for joining this explainer.